Cement manufacturing is a complex process that begins with mining and then grinding raw materials, primarily limestone and clay, into a fine powder called raw meal. This powder is then heated to a sintering temperature as high as 1,450 degrees Celsius in a rotating kiln. At these high temperatures, the original chemical bonds within the raw materials break down and recombine into new mineral compounds. The end product of this thermal process is known as clinker, which forms as rounded nodules between 1 millimeter to 25 millimeters in diameter. Once cooled, the clinker is ground again in a cement mill, where it's combined with gypsum to control setting time. This produces the final fine gray powder we know as cement. When this cement is mixed with water and aggregates like sand and gravel, it forms concrete, the most widely used construction material in the world. But what exactly goes into this transformation? How do raw earth materials become the backbone of bridges, skyscrapers, dams, and highways? Hello, welcome back to Civil Engineering Edge. In this video, we'll explore the 6 critical stages of the cement manufacturing process. 1. Mining and grinding raw materials. 2. Heating in a rotary kiln. 3. Clinker cooling and cement grinding. 4. The final cement product and quality assurance. 5. Various types of cement and their composition. 6. Specific uses of different cement types. Whether you're a civil engineering student, construction professional, or a curious learner, this video will give you an in-depth understanding of one of the most vital materials in our modern world, cement. Let's begin by understanding how we extract and prepare the raw ingredients for cement production. 1. Mining and grinding raw materials. Cement manufacturing begins deep within the earth with the mining of limestone, clay, and other natural minerals. These raw materials provide the essential oxides that form the chemical base of cement: calcium oxide Ca from limestone, silica COs and alumina alco from clay, and iron oxide FeO from iron-bearing materials. The most common mining method is open-pit quarrying. Large drilling machines, excavators, and blasting techniques are used to loosen massive rocks. These are then loaded into dump trucks and transported to the crushing plant. At the primary crusher, the materials are reduced to manageable sizes, typically below 100 millimeters. After this, the crushed material is transported to secondary crushers or grinding mills, where it is finely ground into a uniform powder, known as raw meal. Grinding is done using ball mills, vertical roller mills, or hammer mills, which operate with steel balls or rollers to reduce particle size to about 90 microns. The raw materials must be finely ground for proper chemical reactions during kiln heating. Throughout the process, automated weighing systems and online analyzers monitor the exact chemical composition. The goal is to achieve a consistent proportion of raw meal, usually in the ratio of 75 to 80% limestone, 20 to 25% clay or shale, small percentages of corrective materials, iron or bauxite, etc. This finely ground, chemically controlled raw meal is stored in mixing silos where it's homogenized by air blending or mechanical stirring. Uniformity at this stage is critical because any inconsistency here can affect the chemical reactions during heating and the quality of the final cement. Only after this rigorous preparation does the material move on to the next major stage: thermal transformation in the kiln. 2. Heating in a kiln. The homogenized raw meal now enters the rotary kiln, a massive, cylindrical steel structure lined with heat-resistant bricks. The kiln is typically 60 to 90 meters long and slightly inclined to allow gravity-assisted movement of the material. The kiln process consists of 3 thermal zones. 1. Preheating zone. The raw meal is first passed through preheater cyclones, where it is exposed to exhaust gases from the kiln. This raises the temperature of the raw meal to about 800 degrees Celsius, removing moisture and preparing it for chemical changes. 2. Calcination zone. At temperatures around 850 degrees Celsius to 1000 degrees Celsius, calcium carbonate CaCO decomposes into calcium oxide CaO and releases carbon dioxide CO in a process known as calcination. 3. Clinkering zone. At 1400 degrees Celsius to 1450 degrees Celsius, the material undergoes partial fusion and chemical transformation. Here, minerals combine to form tricalcium silicate CYS, decalcium silicate CAS, and other compounds that give cement its strength. The kiln is fired by coal, natural gas, or alternative fuels like biomass or waste-derived energy. Its continuous rotation ensures the raw meal mixes thoroughly and undergoes uniform heating. The product exiting the kiln is molten clinker, which quickly solidifies into small, gray nodules as it passes through a clinker cooler. This cooling process captures excess heat for reuse, improving energy efficiency. The now solid clinker is ready for the final transformation into cement. 3. Grinding and mixing. Clinker from the kiln is cooled and sent to the cement grinding mill, where it's transformed into the final powdered form of cement. The clinker alone isn't enough, so it's blended with 5% gypsum, which regulates the setting time of cement. Depending on the desired properties, the clinker may also be mixed with fly ash, a pozzolanic material from thermal power plants. Ground granulated blast furnace slag GGBS, limestone powder. These additives improve strength, durability, and workability while reducing the carbon footprint of cement. Grinding is done using closed circuit ball mills or vertical roller mills, where the mix is ground into a powder with a particle size below 45 microns. The fineness affects the rate of hydration and strength development of the cement. Once ground, the cement is conveyed to silos for storage. Modern plants use automated control systems and online particle size analyzers to ensure consistent quality and performance. The result is a uniform, high-strength binding material ready to be packed and shipped to construction sites worldwide. 4. Final product. The final product is a fine, gray powder with immense structural power cement. This powdered substance is stored in silos until dispatched either in 50 kilograms bags, big bags, or bulk tankers. But cement is more than just powder. It's a hydraulic binder, meaning it reacts chemically with water to form a rock-like mass. This reaction is called hydration, and it gives cement its strength and durability. When cement is mixed with sand, gravel, and water, it forms concrete, the world's most used building material. The chemical compounds formed during clinker production, like tricalcium silicate CYS and decalcium silicate CS, react with water to produce calcium silicate hydrate CSH gel and calcium hydroxide, which bind the aggregates together. To ensure quality, cement undergoes various tests before it leaves the factory. Setting time tests: initial and final. Fineness test: Blaine air permeability method. Compressive strength test: consistency and soundness tests. Only when cement meets BIS is 269 or is 1489 or equivalent standards is it released for distribution. The durability of highways, bridges, airports, and high-rise buildings depends on this quality control. Without precise grinding, testing, and packaging, the performance of concrete would be compromised. Thus, the final product, though simple in appearance, is the result of engineering precision and controlled chemistry. 5. Types of cement. Different construction needs require different types of cement. Here are the most commonly used types. 1. Ordinary Portland cement OPC. Available in grades 33, 43, and 53, OPC is used for general construction. The number represents compressive strength after 28 days in MPa. 2. Portland Pozzolana cement PPC. Made by blending OPC with pozzolanic materials like fly ash. It has better resistance to chemicals and is more durable for long-term projects. 3. Rapid hardening cement (RHC). Develops strength quickly used in roadwork or precast concrete where early strength is vital. 4. Sulfate-resisting cement (SRC), resistant to sulfate attacks used in marine structures, sewage works, and foundations. 5. White cement, produced with low iron content. Used for decorative purposes and tile adhesives. 6. Low heat cement. Generates less heat during hydration used in mass concrete works like dams. 7. Hydrophobic cement. Coated with water-repelling chemicals ideal for monsoon-prone or coastal storage conditions. Each type of cement serves a unique purpose, and selecting the right one is crucial for structural integrity, durability, and environmental resistance. 6. Uses of cement. According to their types, cement usage varies based on structural requirements and environmental conditions. Let's understand which type is best for what. OPC 33, 43, 53 grades, used for high-strength or CC works, industrial floors, and high. Grade 53 is used where fast strength gain is required. PPC, preferred for residential buildings, dams, and structures exposed to moisture due to low heat of hydration and high durability. Rapid hardening cement. Used for highway repairs, airfield runways, and precast concrete work where quick strength gain is essential. Sulfate-resisting cement. Ideal for coastal regions, underground pipes, marine works, and chemical industries. White cement. Widely used in floorings, architectural designs, precast walls, and aesthetic finishes. Low heat cement. Essential for massive concrete pours like gravity dams, where thermal cracking due to high heat of hydration must be avoided. Hydrophobic cement. Useful for regions with high humidity or rainfall, especially where long storage is expected before use. And that's how cement is made from raw rock to robust construction. Cement may appear simple, but it holds together the infrastructure of our world. If this deep dive helped you understand the complete process, like, share, and subscribe to Civil Engineering Edge. Don't forget to press the bell icon for more engineering insights every week.